Okay, we've got a roller coaster here, and here's roller coaster 1, and this is going to be 2 right here. So here's roller coaster 1. It's going to start at rest at the top of this hill right here. Gets a little tiny nudge, and then it comes down. Gravity pulls it down. It's moving really fast right here. It's going to drop 7 meters. And then it's going to collide with roller coaster 2, and they're going to stick together. And they're going to move off together as one object. And what we want to know is, what is the final velocity of these 2 roller coasters? Now let's say that the M1 is 1,000 kilograms and M2 is 2,000 kilograms. Okay, and could you guys close the door over there? Thank you. All right. So, now one of the things you need to do when you look at a complicated problem like this one is kind of classify the problem. What are the big physical ideas that are going on here? And well, one of the things you see here is that object 1 is going to collide into object 2. So that's collisions. And right away I think momentum. Whenever I see a collision, I think momentum. Conservation of linear momentum. Okay. And then over here I've got something starting at the top of a hill, and it comes down. There's no friction or anything. It comes down. And in that case, I think energy. If I want to know how fast this thing is going at the bottom, I think energy. And knowing that, having an intuitive sense of whether it's momentum or energy or kinematics or force or whatever, it just comes from practice. From working lots and lots of problems and a lot of thinking. So thinking and practice and working problems and making sure that you understand the problems that you're solving, okay, and not just, getting credit for them. So let's go ahead. Now, I want to know what this final velocity is, and I know that if I use conservation of momentum, I'll get that. So I'm going to start with what I'm trying to find. I know that the initial momentum of my system is going to be equal to the final momentum of my system. And what is the momentum before the collision? Well, this car's at rest, so it has no momentum. But car 1 has momentum, and so this is going to be M1, V1, and then after the collision, they're going to move off together as one object. And so I'm going to combine their masses. So it's the combined mass times that final velocity that we're looking for. Okay. And so this gives me, conservation of momentum gives me an expression I can use to solve for what I'm trying to find. In fact, I can do that right now. I can say, okay, the final velocity is going to be equal to M1 times the velocity of the first roller coaster right here, but just before the collision, divided by the total mass. Okay, now let's take a look at what I know. What do I know? Well, I know what the masses are. Those are given. But I don't know, let me write that better. I don't know what this velocity is. So I can't solve the problem unless I figure out what that velocity is. So now that's when I go with energy, and I say, okay, well, I need to find this. How am I going to find it? Well, the energy that we start with is going to be equal to the energy down here. I'll call that E final. And what kind of energy does the roller coaster have at the top? Well, it has M1 GH, and that's going to be equal to 1/2 M1 V1 squared, the kinetic energy. So it's going to lose all its gravitational potential energy, and it's just going to turn into kinetic energy. Does that make sense? Okay, from Unit 3. So these masses cancel. Well, let's solve for the velocity. So V1 is going to be equal to, we'll multiply both sides by 2. So I have 2GH, and then get rid of V1 squared. I take the square root. And that's going to give me V1 equals the square root of 2 times G times H, which is given to be 7 meters. So let's just go ahead and calculate that. 2 times 9.8 times 7 equals 137.2, and then I'm going to raise that to the power of 0.5, which is the same thing as taking the square root, and I get 11.7 meters per second. So now that's what this is. So now I can solve for V final equals M1, which is 1,000 kilograms, times V1, which I just got to be 11.7 meters per second. And I'm going to divide that by the combined mass, so that's 1,000 plus 2,000. I'm just going to write it as 3,000 kilograms. That's the total mass. And now I can get that. So I'm going to multiply that by times 1,000, and then divide by 3,000. And I get 3.9. meters per second. Okay. And that's how you do it. Let me zoom out. Now let me ask you this. So in this problem, from here to here, from the roller coaster at the top to the roller coaster at the bottom before the collision, energy, mechanical energy, is conserved. Then during the collision, momentum is conserved. But let me ask you this. During the collision, do you think kinetic energy is conserved? And the answer is no. Whenever you have a perfectly inelastic collision, that is, one object collides with another and they stick together, you've actually lost the maximum possible amount of kinetic energy for that. That's why I call it a perfectly inelastic collision, which we talked about last week. Now let's actually figure this out. What is K initial? Well, K initial is, well, I'll just go ahead. 1/2 M1 V1 squared. Now, you didn't really have to do this, but this is 1,000 kilograms, and the velocity at the bottom was 11.7 meters per second. Let's square that. So the initial kinetic energy, well, 1,000 divided by 2 is 500 times 11.7 squared, and I get 68,445 joules. You probably should round that off, but it doesn't really matter. Now, what was the final kinetic energy? Well, it's 1/2 the total mass times that final velocity squared. So this is equal to 1/2 3,000 kilograms times 3.9 meters per second squared. And so let's figure out what the final kinetic energy is. 1/2 of 3,000 is 1,500 times 3.9 squared. And I get 22,815 joules. So we started off with this much energy, and we ended up with this much mechanical energy. We lost most of our mechanical energy. Where did it go? Well, when those two things collided, they made a big loud sound. They went crunch, and they also vibrated their molecules randomly. So, and then we call that thermal heating. And so whenever you have an inelastic collision like that, you're taking some of that really nice, orderly kinetic energy and converting it into the randomized kinetic energy, which we call thermal energy. And so it's just kind of, and that just kind of gets radiated out into the environment. So it's not, it doesn't disappear, but it's rendered useless to us. Okay. Any questions? Okay. That is all.